Hello dear students, I Ganesh welcome all of you to this session of plus 2 second year mathematics, and today the topic of discussion is on relation and function. Already in our previous classes we are defining what is a function, we are defining the properties of the function, we are defining the inverse of a function. A function is invertible or not, that we are defining in our previous classes. But today it is somehow different, and today we will bring a new concept of function, that is composition of functions. So today the topic of discussion is on composition of functions. Composition of functions. So you see what we mean by composition of functions. Okay, let us begin with a real life situation. Okay, because mathematics is full of real lives. It contains the real life fundas in mathematics. So let us connect it, the composition of a function, with a real life situation. Then we will come to the definition. Okay, so let us begin with the composition of function. You see, suppose in a real life, suppose we are in the city of Berhampur. Okay, so this is our current city. So we are in the Berhampur. Now we are interested to travel Delhi. Okay, so our destination is Delhi, from Berhampur to Delhi. So what we do? You see, suppose there is no train is available for the traveling from Berhampur to Delhi. Okay, so on that day, on our traveling day, there is no train is available from Berhampur to Delhi. So what we do? We see that there is a train from Kolkata. So what we do? We have to travel from Berhampur to Kolkata and then Kolkata to Delhi. Unnecessarily we have to go to Kolkata. We are not interested. But since there is a train from Kolkata to Delhi, so we have to cover our journey in two parts. One is from Berhampur to Kolkata and the Kolkata to Delhi. So indirectly we have to travel from here to here. Okay, if it is the one part, say it is the set A and it is the set B and it is the traveling is considered as a function. So Berhampur to Kolkata, that is the first function. Okay, and then the second function is next the second travel is from Kolkata to Delhi. So in this way we have to cover the journey from Berhampur to Delhi. Yes or no? Obviously we have to cover like this. So you see, so the total journey of Berhampur to Delhi, now it is a mixture of two journeys, two destinations from Berhampur to Kolkata and Kolkata to Delhi. Yes or no? So this mixture, this way to cover the whole journey is called as composition. It is called as composition. So my dear students, composition means what? Composition means mixing of some functions to create a new function. Okay, so that is the meaning of composition. So my definition of composition of functions means, what do we mean by composition? Now we go for the definition and we will go in detail. So you see what I say, composition is a mixture or composing of two or more functions, to get a new function. Okay, so in this way the composition of functions is created. Now if we say mathematically what the composition is doing, if let f is a function from a to b, let f is a function from a to b, and let G is the function from B to C. Okay, f is a function from A to B and G is a function from B to C, defined as f of x equals to y, where x belongs to A and y belongs to B, and G is from B to C is defined as g of y equals to z, where y belongs to where? Y belongs to B, we all know already, and z belongs to where? Z belongs to C. Then we say the composition is denoted as G operation F. G operation F. And how it is defined? It is defined from A to C as, we are reading it as GOF. G operation F, we are reading it as GOF x equal to z. Okay, so in this way the composition function GOF is defined. Okay, my dear students, so you see the composition function GOF is defined from A to C, and what it do? It converts the elements of x to the element of C, that is z, by through B. Okay, let us again we will go to that one and we see it how the composition is done. Okay, so I am erasing this one. So you see GOF of x equals to z means what? You see it implies that is g of f of x equals to z, or we say g of y equals to z, in this way. So in GOF function you see the functional value of one function is behaving like a parameter of the second function. You see originally x is there, now f of x, here you see f of x is behaving like a parameter, is behaving like a variable of the second function g. Yes or no? So g of f of x equals to z means what is f of x? F of x is y, it is the functional value of x. So here g of y equal to z. So what we can say? We can say so my dear students, you see we can say in composition of functions, one functional value is present as a parameter, of the second function or some new function or some other function. Okay, so in this way the composition of functions is defined. In this way the composition of functions is defined. Okay, my dear students, so this is about the composition and the way to define the composition, what it means. Similarly, we can compose not only two functions, we can compose a function with itself, we can compose some other functions. Okay, and you see similarly we can say, as here GOF is defined, GOF of x as z, which is evaluated like this. X is there, then f is applied, it is f of x, and on f of x g is applied. So it is g of f of x equal to z. Similarly, we can say what is it is called as, what we can call it? We can call it as fog x. So what it means? So it is equals to f of g of x. Okay. So you see, initially x is there. On x, g is applied. Then on g of x, f is applied. So it is f of g of x. So this way our composition fog x is defined. Okay, my dear students. So you see some of the compositions of two functions. One is gov and another is fog. And we can write similarly. Similarly, we can say what is fog x? It is f of x. So here you see, on x f is applied, and on the next value again f is applied. So f is applied on the itself like this. Okay. And similarly, what is h operation, g operation, fx? So what it means? It means h of g of f of x. So it means like this. So initially x is there. On x f is applied. Then on the total value g is applied. Then on the next, the total value is behaving like a parameter of the variable of the function h. Initially x is the initial parameter. On it f is applied. On the total value, which is behaving like a parameter of the function g. Again on the total value, which is behaving like a parameter of the function h. So the final result or the total result, which is called as composition. Here the composition is done on how many functions? It is done on 3 functions. So in this way we can define the composition of functions. Okay. Let us we will go for some of the examples of composition, and we see how the composition can be evaluated. Next on, we will go for the composition of more than one function, and we see how the composition is evaluated. Okay, my dear students, you see with some examples. So we are going for some of the examples. Please make note of these things. Those are very crucial for you, how the evaluation is done. So we will go for some of the examples, you see. And what we observe there, we make a note of those things. Okay. So some of the examples are: find fog and gov. Fog and gov. These are the examples in our books also. You can find this type of examples from your books. Find fog and gov where f of x equals to x cube plus 1, g of x equals to x square. Suppose this is one example. So we have to find fog and gov. So fog means what? Fog means the composition of f with g. Initially, so we will go first fog. So fog, it is a composition of f on g. Okay. So f is operating on the functional value of g. So that is, it is equals to f of g of x. It means initially x is there. On it g is applied. That is g of x. Okay. And on the total value f is applied. So you see how it is evaluated. F of. Now if g is applied on x, what is the functional value of g of x? You see the functional value is x square. Okay. So now this functional value is behaving like a variable, is behaving like a parameter of the function f. And how we can evaluate it? You see, whenever f is applied on a parameter x, it converts it in the format of x cube plus 1. In this condition, the result is obtained. So now f is applied on x square. So how it converts? It converts this value as cube of the x square plus 1. So what is the result? It is x to the power 6 plus 1. So this is the way to define our result fog x. Now can we define gof x? Yes, my dear students, please try to think how to find gof x. Yes, you are correct. It is what? It is g is applied, g is operated on the functional value of f of x, that is g of f of x. Clear? And how we can evaluate it? What is f of x? You see, the value of functional value is x cube plus 1. And what the g do? G converts any variable in the form of its square. Okay, so on it is applied, so it will convert it as square of the value x cube plus 1. So in this way our gof function is defined. So my dear students, you see both fog and gof. Clear? So you can see that how fog is defined, how gof is defined. Okay, so my dear students, you can observe something, that fog is not equals to gof. So the functionals are not equal. So my dear students, when the functions are equal, if they are having same domain and same codomain, and their functional values are equal. So here the functional values are differ from each other. So we can say that fog is not equals to gof. Okay. Next we go for another example, and what I hope you can find this type of functional values, this type of composition values. Okay. So I am cleaning this one. Suppose we change the functions as, and we will go for another example. Find gof, and where we are changing the functions. Okay, where f of x equals to, suppose it is sin x, and g of x equals to x fifth. Okay, suppose in this way we have to, the functions are mentioned and we have to find their functional values. F of x is defined as sin of x. G of x is converting, means g of x is defining as x to the power 5. Now, can we able to find fog? Can we able to find gof? And if yes, how it can be defined? You see, initially we will go to evaluate fog x. That means x is initially present as a variable. First of all, g is applied. Then on the total value, f function is applied. The total functional value of g is behaving like a parameter of the function f, that is f of g of x. Clear? Now it is f of, what is g of x? It is x to the power 5. Okay. Now if x to the power 5 is there, and if functional value f is applied on it, okay, now what is the conversion? It can be converted as sin of x to the power 5. Okay. Next, can we define gof x? Yes, we can define gof x as g of f of x. Okay, and how the evaluation procedure? It is sin x, and you see, if a variable is there, if sin x is behaving like a variable of the function g, what g do? G converts all the variables as the fifth power, as x to the power 5. So here sin x will convert as by g as sin x to the power 5, or we can write it as sin of x. Yes or no? So in this way we are defining our composition functions. Clear, my dear students? Now let us move to some other examples. Okay, and later on we will see about the conversions. Next we will move for another example. I am cleaning this one. So another example is there. Find fog and gulf. Okay. When f equal to 1a, 2b, 3c, 4d, and g equals to A5, B9, C4, D8. Clear? Suppose in this way the functionals are defined. F is defined and G is defined. So we have to evaluate fog and gulf. Let us see whether we can able to find fog and gulf in these cases. So let us go with some pictorial mode. It will clarify to a great extent. Okay. So you see F is containing this type of pairs. The order pair 1a. What it means? That means the function f has the domains elements as 1, 2, 3, 4, and the function f is converting them to the value of a, b, c and d. Okay, my dear students. Now what the function g do? The function g again converting them, those functional values which are behaving like the parameter of the function g can be converted to the value of 5, 9, c is converting to 4 and d is converting to 8. Okay, it is like this. Okay, so can we able to find fog and gulf in these cases? Okay, can we able to find fog and gulf? You see, yes, please go through it and try to find fog and gulf. Okay. Okay. So let us see here fog. Fog means what? Let us first initially we will go to find fog. So it is f of fog x means it is f of g of x. Clear? So f of g of, what are the elements of g? So it is g of a. So it implies we will go one by one. So f of g of a means f of 5. You see f of 5 is not evaluated. F of 5 cannot be evaluated because f does not have this type of domain values. So this is not evaluated. So the fog is not defined in this case. Okay. You can see if you go for similarly if you go for the element b, which is a variable of the function g, f of g of b means what? It is f of 9, but 9 is not a domain value of f. Okay, so this is not evaluated. So this fog function cannot be composed. Here f and g cannot be composed. Now, or we can say f cannot be operated on g. Okay, my dear students. So can we operate g on f? Let us check it. So now we are going to find our gulf x. What it means? It means it is equals to g of f of x. So we will go with one by one element. The elements of f are, initially it is applied on 1. So it is g f of 1 means what? It is g of f of 1 is a, and you can see a is a parameter of the function g. So what is g of a? G of a is 5. Now what is similarly, if it is g of 1, we can say, now what is g of 2? So it means it is f of 2, and it is g of f of 2 means it is g of b, and the result is 9. Similarly, what is g of 3? It is g of f of 3, and g of f of 3 means it is c, and it is 4. And what is g of 4? It is g of f of 4, and what is f of 4? It is g of d, and what is g of d? It is equal to 8. Now you can see, though fog function is not defined, Gauss function can be defined at here. And what the Gauss function do? The Gauss function able to convert the elements, able to compose the elements, and we can write Gauss as. We can write Gauss as the order pair 1, 5 means by which 1 can be convertible to 5. We can write 2, 9. We can write 3, 4 as the ordered pairs. We can write 4, 8 as the ordered pairs. So in this way, the Gauss function can be defined. Okay. So it is now clear that fog and Gauss cannot be defined simultaneously. If it is defined, then fog or Gauss may not be equal with each other. Okay. So you see, this is a example of composition of functions. Look carefully, my dear students. Okay. Now I am cleaning the board and I am writing some of the observations, some of the results of the compositions. So, the first observation is, make a note of those observations. Okay. The first note is, if f and g are any two functions, then fog is not equal to Gauss. Okay, fog is not equal to Gauss. That is composition of functions. That is composition of functions is not commutative. Is not commutative. The next one is composition of functions. Composition of functions is associative in nature. Is associative in nature. It is very important. Though it is not commutative, but it is associative. What it means? That is, H operated on G operated on F, it is equals to H operated on G operated on H. Okay? Clear? So, these two are very vital informations about the composition of functions. Next, we are going to prove a result which is very vital for you. Okay? Next one is, an important result is there. If f is from A to B, if f is defined from A to B and G is defined from B to C, if f is defined from A to B and G is defined from B to C, are any two bijective functions. We remember about the bijective functions, means it is both 1 and on 2. It is the condition. Okay, if f is from a to b and g is from b to c are any two bijective functions, then we have to show GOF is from a to c is also bijective, and GOF inverse equals to F inverse operated on G inverse. Okay, so this is very important. Okay, as per your exam point of view, always this result is appeared in many of the exams, that if F is from A to B and G is from B to C are any two bijective functions, and we define GOF from A to C. Obviously GOF is from A to C, that is also bijective in nature. And what is the final result? The inverse of the composition, that is GOF inverse, is nothing, it is F inverse operated on G inverse. Okay, so let us try to prove this result. So we are going for a proof of this result. Okay, you see, we are going to prove this result. So what is given here? Solution, we are going to write the proof. Here F is from A to B and G is from B to C are the what? Are the bijective. Are the bijective functions. Okay, and we know that composition, if the original functions are bijective, then their composition is also bijective. That implies GOF from A to C is also bijective. If the initial functions are bijective in nature, their compositions are also bijective. And as it is bijective, hence inverse of, if it is bijective, then only we can find the inverse. Hence inverse of GOF will exist, otherwise we can't find the inverse of GOF. So inverse of GOF is exist, and GOF inverse, if initially GOF is from set A to set C, then GOF inverse is from, it is a reverse process, so it is from C to A. Okay, so you see the inverse function is from C to A. Clear? Okay. GOF inverse is from C to A. Now we will go for about the, so GOF inverse is now defined. Now we are going to find, as we know F is also bijective, G is also bijective. So we can see, or we can write, as F is from A to C, A to B, and G is from B to C are also bijective, therefore they are inverse functions. Therefore they are inverse functions also exist. Okay, so their inverse functions also exist. And if F is from A to B, as F is from A to B, Okay. So F inverse, then F inverse is from B to A is also bijective. Okay, is also bijective. G is from B to C, then G inverse is also from C to B is also bijective. Clear? So now we are able to define inverse of F. We are able to define inverse of G. Okay. Now we will compose them. You see, therefore, G inverse operated on F inverse. You see, G inverse operated on F inverse, or we can say your F inverse operated on G inverse is from C to A is defined and bijective Okay, so you see both the functions, one is Gauss inverse and F inverse operated on G inverse, both are from set C on set A. Clear, my dear students? So in this way we are able to define these two functions, and now we can verify that both functions are having the same domain and they are having the same codomain. Though the formats are different, but the functions are having same domain and same codomain. Yes or no? It is from C to A. Means the domain of this function is C, the codomain is A. And here also the domain is C and codomain is A. Okay? So now we are able to define these two functions. Now we have to show the functional values are same, because two functions are said to be equal when the functions are said to be equal. Yes, if they are having the same domain and same codomain and the function values are equal with each other. So now we are going to show the functional values are equal with each other. Okay. So now we are moving to show the functional values are equal to each other, and I am writing here also Gauss inverse, that again I am indicating here Gauss inverse is from C to A. Okay. For it now to show what we do, let us consider x belongs to A, some element x is belonging to A, y is belonging to B, and z is belonging to C. Okay, this is about the elements belonging to set A, y is belonging to where? Set B, and z is belonging to set C. Okay, so therefore we can say f of x is equal to what? As f is from A to B, so f of x equal to y. Yes or no? And g of y equals to what? We can say g of y equals to z. That implies f inverse y equal to x. Clear, my dear students? F inverse y equals to x, and g inverse z equal to how much? G inverse z equal to y. Okay. Now we will check what is Gauss and how it rule out. Therefore, Gauss x, the composition, it is g of f of x, so it is g of y, which is equal to z. That implies as Gauss is converting x to through y in the form of z, so that implies Gauss inverse is from where? Is from Gauss inverse z equal to x. Okay. So I am going to show it again. You see, I am cleaning the board now. So it is G of inverse z is equal to x. Clear? Now again I am writing this one. What I am writing it here? As we define, so what is G of x? It is g of f of x. Again I am writing for your clarity. So you see initially x is there, but I am writing it there. Again I am writing. So you see x is there and f is applied on x as g of f of x. So it is equal to what? It is g of y. And what the g function do? It converts y, the parameter y, to the form of z. So you see by the function g of x is converting to z. Yes or no? X is converting to z. But you can see that g of function is a bijective function. Already it is shown. So we can say g of inverse. What the g of inverse do? It converts z as x. Since as it is bijective, so its inverse can exist. And what the inverse do? The role of inverse is defined. It is a reverse process. Yes or no? So it converts the elements, the image elements, to their pre-image values, to their original values. So here the composition function converts the image value to its original pre-image value. Okay? So I am cleaning this one. Clear? So you see G function is now defined. What is its image and how it is defined. Again, we are going to show F inverse operated on G inverse. Now you tell me, G inverse is operated on what type of elements? G inverse is operated on Z. Okay? Yes or no? And what it do? It is equals to F inverse of G inverse Z. And it is equals to F inverse. What is G inverse Z? We can write it Y. And what is F inverse Y? It is again X. So you see, my dear students, the inverse function G of is converting Z to X. This composition F inverse operated on G inverse is also converting Z to X. And both are having, previously so both are having the same domain and same codomain. Yes or no? So from here it is clear that though the representations are different, the functions are equal with each other. Hence we say G of inverse, it is nothing, it is equal to F inverse operated on G inverse. Okay? So this is one of the important result of the composition. Okay? So today we observe about the composition of functions and how composition can be done. Yes or no? That we observe today. Now we move to a new concept. Okay? We move to a new concept of function, that is about okay, even and odd function. Even and odd function. Okay? So today we will discuss about the even and odd functions. So even, we know about the even number, but even function is somehow different and odd function is somehow different. So now I am going to tell you about the concept of even and odd function. So we can say any function f of x is said to be an even function if f of minus x equals to f of x. Means what I put as a functional value of x, the same result, the same functional value obtained, though I replace x by its additive inverse minus x. Okay, so f of x and f of minus x remain same. Later on we will go for an example. And any function f of x is said to be odd. Is said to be odd. When a function is said to be odd function, if f of minus x, it is equals to minus of f of x. If this is the result, the function is said to be odd. Okay, so in this way the even and odd functions can be defined. The even and odd functions can be defined. We will go for an example. Okay, consider f of x equals to x square. Okay, and you see, if I replace x by minus x, what I obtain? It is square of the value minus x. Yes or no? So you see, square of the value minus x, it is nothing, it is equal to again x square. Clear? You can see. Okay, so the functional value as x is getting x, we are getting it as x square, and for minus x also we are getting it as x square. The both are having the same value. Yes or no? It does not alter, it does not change its value. So if the function having same functional value as x or as minus x, it is said to be what? It is said to be an even function. So f of x equals to x square is an what type of function I can say? Yes, it is an even function. Okay. Now we go for an example of odd function. Consider f of x equals to x cube. Okay, we are considering f of x as x cube. Now what is f of minus x? It is cube of the negative value minus x. So it is minus x cube. Yes or no? So you see, what is the functional value of x? And here what is the functional value of minus x? It is somehow minus is there and it is equal to minus x cube, or I can say it is equals to what? Minus of the original value. Yes or no? So you can see that if I change the parameter, the functional value also changes, and changes to what? Changes to a with a negative sign. Yes or no? So if this is the case, so here f of x equals to x cube is an what type of function? Is an odd function. So this is the concept of an even function and a odd function. Okay, so my dear students, please look it. Okay, so I am going to clean it. And we can take many type of examples of even function also. Now suppose somebody asks you that there is a constant function f of x equal to 5. Now my question is it an even function or an odd function? Yes, my dear students, you are correct. Your imagination is totally correct that it is an what type of function? It is an even function. Why? Because if I replace x by minus x, if the parameter changes, as it is constant, the value is remaining the same. Okay, it does not alter, it does not depend on the value of x. So the constant function is always what type of function? It is a even function. Okay, so I can make it as a note. Every constant function is an what type of function? Is an even function. Okay, the next one is every real function can be expressed by the sum of an even and odd function. This is very important. Every real function can be expressed by the sum of an even and odd function. Okay? What it means? It means if a function is there, then we can split it, we can convert it, or we can represent it by the sum of two expressions, out of which one is behaving like an even function, and the other expression, the other representation is behaving like an odd function. Okay? How you see? Or we can see, if f of, mathematically we can write it, that is, if f of x is the given function, then f of x can be represented as like this. Okay, so it can be represented like this. For your clarity, I am putting it in bracket. Okay, you see what I write it here, it is representing an even function. This type of expression is representing an even function, and this type of expression is representing an what function? It is representing an odd function. So you see, our total function is expressed by the sum of two functions. One is even and another is odd. So it is an what type of function? It is an even function. And what is this one? This is an odd function. So we can say every function which is a real one can be expressed by the sum of an even function and an odd function. For a clarity, okay, let us take an example. Okay, sometimes we are getting the questions, the problems are like this: convert it or represent it by the sum of an even and odd function. So let us take an example. Represent this expression, which is containing an exponential function and a trigonometric function, e to the power x plus sin x, by the sum of even and odd function. That is what we have to represent by the sum of an even and odd function. So how to represent? So I am going for the solution. First of all, what we do? We have to convert, or we have to represent the expression as f of x. So here, what is f of x? F of x equals to e to the power x plus sin x. Clear? And if it is f of x, what is f of minus x? If function is converting x in this format, so what is f of minus x? It is e to the power minus x plus sin of minus x. and it is equal to e to the power minus x minus sin x. Clear? As we know, sin of minus x equals to minus sin x. Now, as we know, as we say that it can be convertible, so here, okay, I am cleaning this portion now. You see here, f of x plus f of minus x divided on 2, what is its result? You can see that if I am going to make a sum of it, this plus sin x and minus sin x are going to be cancelled, and we are getting e to the power x plus e to the power minus x divided on 2. Clear? And similarly, what is f of x minus f of minus x divided on 2? If we are going to make a subtraction, we are getting the result as e to the power x minus e to the power minus x plus 2 sin x divided by 2. Okay? So, we can say that this function, which is expressed as e to the power x plus sin x, is convertible or is represented as the expressions like this one plus this one. And this is an what? This is an even function, and this is an what? This is an odd function. You can verify also. How to verify? Put x with its negative sign, then you can see the result remains same in this case. So this one is an even function. I can represent it also as g of x, and this one as h of x, where g of x is what? Is an even function, and h of x is what? H of x is an odd function. Okay? So, this is about the technique or about the procedure to express a given function by the sum of an even function and odd function. Okay? So, you see, we can get many questions, we can solve many questions by this type of technique. Okay, my dear students? So, this is about the even and odd function. With this, I can say that today we are discussing about composition of functions, and we are able to show how to represent a function by the sum of an even and odd functions. Okay, so dear students, with this we rested here. Thank you, and thank you to all. Goodbye.